Okay, so this video is going to be a continuation of a prior video where we had started working on a collision problem. The problem is shown here. So the problem entails a mass or a particle of mass m hitting an inclined plane with a velocity v0, and the inclined plane is resting on a horizontal surface, and it can slide on the horizontal surface without any friction. The inclined plane makes an angle theta, and the coefficient of restitution between the particle and the inclined plane is E, and the question was to determine the velocities of the particle and the incline after the impact. So the particle is of mass m and the incline is of mass 2m. So in the prior video, or part 1 of this problem, we had discussed how to derive the impulse momentum equations, and then how to derive from there the conservation of linear momentum equations. One of the important observations based on the impulse momentum equations was that in a problem like this, we need to understand that here this is a special type of a collision problem, in the sense that this incline is not allowed to move in the vertical direction. Its motion is constrained only in the horizontal direction, and so essentially what is happening here is that there is along the vertical direction an infinite inertia or infinite mass, in this case the mass of the ground, which can be considered infinity, which is blocking the motion of this incline. And when this happens, we have discussed that the while the conservation of linear momentum is applicable in any direction for these problems, if you take any direction which has a component along this vertical where the motion is blocked, then we don't get a usable conservation of linear momentum equation. So what we have to look for in problems like this is a direction where there is no restriction in motion. So in this case, the motion is unrestricted along the x-axis or in the horizontal direction, and so the conservation of linear momentum equation has to be written in this horizontal direction. And we have derived that. We started with impulse momentum equations, and we showed that the conservation of linear momentum equation can be written for the horizontal direction, whereas for the vertical direction we see that there are some unknown impulses that will show up in the linear momentum impulse equation. So that is where we left off in the prior video, and now what we'll do is so if you consider this problem again, and in particular if you consider this free body diagram where we have, or these two free body diagrams where we have shown the velocities and the impulses, you will note that for the velocities to be determined, for the incline there is just a single velocity in the x direction, v2x. For the particle, it can have velocities both in the horizontal and vertical direction, and we call them v1x and v1y. So essentially there are three unknowns that need to be solved in order to find the velocities after the impact, and so we need three equations, and the linear momentum conservation equation gives us one of those three equations. So we need two more equations. So the second equation that we are going to use is the coefficient of restitution equation. So coefficient of restitution Now the coefficient of restitution is a is a characteristics of the two surfaces that are coming in contact, or the two materials that are coming in contact during collision. It has almost nothing to do, you can consider that it has nothing to do with the inertia or the masses of the particles or the surfaces that are colliding. Rather, it is a property of the surfaces that are undergoing collision. So in this case, and there are various ways to understand what coefficient of restitution is. One way to understand coefficient of restitution is that it is kind of the ratio between the compression impulse and the restitution impulse. So when a collision happens between two surfaces, then there is a slight compression that happens when the two particles have just come in contact, and then when they are separating, then there is another impulse, and that is called the restitution impulse. So it is the ratio between the compression impulse and the restitution impulse that is the coefficient of restitution. But for mathematical formulations, the way we formulate it is the relative velocity of departure divided by the relative velocity of approach. So here is our inclined plane, and so here is the particle. This is the instant of contact. The particle is moving down with a velocity v0, and after the impact, the particle is going to have a velocity v1x, and it's going to have a velocity v1y, and the incline is going to have a velocity v2x. Okay, so this is my x-axis and this is the y-axis. This angle is theta. So here we have to keep in mind that the coefficient of restitution, in order to formulate it correctly, you have to write the coefficient of restitution about the line of impact. So in this case, this is the line of impact. As you can see, this is an oblique collision. The line of impact is the line that is perpendicular to the surface or the plane of contact. And note that this is the plane of contact. And this is the line of impact. So, and the line of impact is perpendicular to the plane of contact. So the coefficient of restitution formulates the ratio of the relative velocity of departure and the relative velocity of approach along the line of impact. So this is an especially important point, that the formulation of this ratio must be done considering the velocities along the line of impact. And why is that? Because really the compression and the restitution impulses are taking place along the line of impact, because it is in this direction that the impulses, the action-reaction impulses, they lie along this line of impact. So the coefficient of restitution is also formulated along that. So now if we formulate this coefficient of restitution, E is equal to the relative velocity of departure divided by the relative velocity of approach. So let's write the expression for the relative velocity of approach first. So the incline is not moving, so it has no velocity during the approach phase of the collision, the particle is approaching the incline with a velocity v0, but we need to keep in mind that our interest is in the velocity components that are along the line of impact. So in fact, the relative velocity of approach is going to be the component of the velocity of this particle along the line of impact. So v0 cosine theta, because this angle you can see from trigonometry, this angle is going to be equal to theta. Okay, so the relative velocity of approach in this case therefore is going to be this angle is theta, so the relative velocity of approach is going to be v0 cosine theta minus 0, and so that is the velocity with which the particle is approaching the inclined plane. Now when we formulate the relative velocity of departure, we should formulate in order to consider that the coefficient of restitution is a positive number. So the fundamental definition of the coefficient of restitution is E is equal to the absolute value of the relative velocity of departure divided by the absolute value of the relative velocity of approach. So since we need to keep these numerator and denominators, both of them need to be positive, one way to ensure that they are positive is to take the square, because E has to be a positive number. It is it is typically E is between 0 and 1. Okay, so E equals 1 is a perfectly elastic collision, and E equals 0 is an inelastic collision. In an inelastic collision, the two colliding objects will stick to each other, and in elastic collision they will bounce off of each other, but there will be no energy loss. For any E not equal to 1, there is an energy loss during the collision process. Now going back to this, because E has to be a positive number, one way to ensure that we are formulating this correctly when we use absolute values is to take the square. However, if you take the square of the relative velocities, then it complicates the expressions. So one way to ensure that the numerator and the denominator remain positive while you do not have to square things is to do the following. If in the denominator you're formulating the relative velocity with which the particle is approaching the incline, then in the numerator formulate the relative velocity as the relative velocity of how the incline is departing from the particle. So in the denominator, if it is what is the relative speed with which the particle is approaching the incline, in the numerator it's going to be at what relative speed is the incline departing away from the particle. So if you do it that way, then the incline is moving with v2x, but we need to consider the component along the line of impact. So it is v2x sine theta. So that is the velocity at which the incline is moving away from the particle, minus the velocity with which the particle is moving after the impact along the line of impact, and that is going to be v1x sine theta minus v1y cosine theta. Okay, so let me write that expression one more time. E is equal to v2x sine theta minus v1x sine theta minus v1y cosine theta divided by v0 cosine theta. Right, and so this is going to be our equations have been numbered so far up to equation 6. So this is going to be our equation 7. Alright, now We can do some quick analysis to see what happens if we apply the coefficient of restitution equation, for instance, along the x-axis. We know that we should not do that. The coefficient of restitution equation must be written only along the line of impact. But say we ask the question, what would have happened if we applied the coefficient of restitution equation along the x-axis? Then what would have happened is that along the x-axis, this particle, which is falling on the incline, does not have any velocity along the x-axis. So the denominator would have been equal to 0. And so if the denominator is 0, then then we would have E equals some division by 0 condition, and that would not lead to that would essentially be an incorrect equation. So it is it's just a verification that indeed your coefficient of restitution equation must be written along the line of impact. So that's important. Now the other, and actually let me just simplify this and write it a little bit better. So we have E V0 cosine theta is equal to V2x sine theta minus V1x sine theta plus V1y cosine theta. Call this equation 8. So now we have two equations. We have the equation that we obtained from the conservation of linear momentum, and we also have an equation that we have obtained from applying the coefficient of restitution on the relative velocities. So we need a third equation, and that third equation would come from the observation that for the particle, if you considered the direction along the plane of contact, there would not be any change in velocities. Okay, why are we saying so? Well, think of the motion of the particle this way. So if this is the incline, think of the situation, or think of the instant when the particle is just about to hit the inclined plane. At that point, well, you can say that the velocity is V0 vertically, but you could also say that the velocity is V0 cosine theta in the in the direction along the line of impact, and V0 sine theta along the plane of contact. So this is the line of impact and this is the plane of contact. Now if I consider the motion of the particle to consist of these two velocities, and we know that at the instant of collision there is going to be an impulse F, I think we called it F delta t. Let me just see here. Yeah, the impulse is F delta t. Then you can see here that the impulse F delta t is going to affect V0 cosine theta for sure, because it is directly opposite to V0 cosine theta. However, F delta t will not have any impact on V0 sine theta. Why? Because it is perpendicular to the V0 sine theta. And that means that the velocity of the particle after the impact along this direction, that is in this case it is the plane of contact, is not going to change. So we make the observation that the velocity of the particle will remain unchanged along plane of contact. Okay, now this is true for two objects that are colliding, provided that there is no restriction in the motion along the plane of contact. Now, if it so happens that of the colliding objects there is one or more whose motion is blocked along the plane of contact, then we cannot make this claim, because if there is a blockage along the plane of contact, that means that there is an impulse along the plane of contact, and so for that particle or for that object we cannot say that its velocity will remain conserved. So the reason I'm mentioning that is that logic applies to the plane. For the plane, for the inclined plane, we cannot say that there is going to be zero change in velocity along the plane of contact. We can say that for the particle, because the particle's motion along the plane of contact is not blocked, but the incline's motion along the plane of contact is blocked, right? So because we know that for the incline there is not only this f delta t, this is by the way angle theta, but there is also a f bar delta t coming from the ground. And so because there is a f bar delta t coming from the ground, there is a component of this f bar delta t along the plane of contact, and so the velocity of the incline along the plane of contact will not remain conserved. So we make a note that at the point of collision, the velocity remains unchanged along the plane of contact for the object whose motion is not blocked along the plane of contact. So this incline, because of the ground constraint, does have a blockage. It does not allow motion to happen freely along the plane of contact, because there is a component of this plane of contact along the ground. Okay, so but the velocity of the particle will remain unchanged. For this particle, the velocity will remain unchanged. Now if we go back to these velocities here, what is that velocity? What is the velocity along the plane of contact just before the impact for this particle? Well, it is, if I consider the direction going up the plane to be positive, then initially there was V0 sine theta, right? V0 sine theta, as you can see, this was going downwards. That's why I'm putting a negative sign, considering up the plane to be positive, and so this velocity will remain conserved. So what is the velocity of the particle up the plane of contact after the impact? Well, it is V1x cosine theta and so this is v1x, this is v1y plus v1y sine theta. Yeah, so that is our equation 9, and this in fact now gives us our third equation. So now we can use our three equations. So I'll write down our equations on the next page and then we'll solve them. The linear momentum conservation along x, that gives us 2vx, or rather it gives us 2v2x equals negative v1x. So 2v2x equals negative v1x. So this was our equation 5. Okay, then we had the coefficient of restitution equation. And this equation is E v0 cosine theta is equal to v2x sine theta minus v1x sine theta plus v1y cosine theta, and this was our equation 8. And then velocity conserved along plane of contact, this is for the particle only, and this gives us negative v0 sine theta equals v1x cosine theta plus v1y sine theta. So this was our equation 9. So now what we'll do is we'll solve these equations. So first what we'll do is we'll substitute for v1x. So therefore from 5 we have E v0 cosine theta is equal to v2x sine theta, and minus v1x is equal to 2v2x, so it's going to be plus 2v2x sine theta plus v1y cosine theta, which gives 3v2x sine theta plus v1y cosine theta. And we also have this equation, equation 9. So we can see that well, equation 9 then becomes, let me check, so equation 9 becomes negative v0 sine theta is equal to, so v1x is going to be negative v2x, 2v2x rather, 2v2x cosine theta plus v1y sine theta. Okay, so let's say this is our equation 10 and this is equation 11, right? So now what we can do is, if we multiply equation 10 with sine theta and equation 11 with cosine theta, right, and if we subtract, then what we'll get is the following. We'll be able to eliminate essentially v1y. So what will happen is we are multiplying 10 with sine theta, so E v0 cosine theta sine theta, that's on the left hand side, and plus v0 sine theta cosine theta, again the left hand side of equation 11, Then we take the right hand side of equation 10 and multiply with sine theta. So that's going to give us 3v2x sine squared theta, plus we will have the v1y cosine theta sine theta, and then we'll subtract from that the right hand side of equation 11 multiplied by cosine theta. So when we do that subtraction, what we will have is, let me just check, yeah, so what we will have is plus 2v2x cosine squared theta. So in other words, v2x turns out to be v0 sine theta cosine theta times 1 plus e divided by 3 sine squared theta plus 2 cosine squared theta. Which is v0 sine theta cosine theta 1 plus e divided by 2 plus sine squared theta. Okay, so that's done. So that is one velocity determined. This is therefore the horizontal velocity of the incline. After the impact, and v1x becomes minus 2v2x, so that is minus 2v0 sine theta cosine theta 1 plus e divided by 2 plus sine squared theta, so that is minus 2v0, or rather minus v0 sine 2 theta 1 plus e divided by 2 plus sine squared theta. So now this is the horizontal component of the particle's velocity after the impact. And lastly, we want to find out v1y, that is the vertical component of the particle's velocity after the impact. One thing that you can see here is that the x component of the particle's velocity after the impact is going to be negative, which means that the particle is rebounding. It's not going in the positive x direction, it's going in the negative x direction. That is kind of expected because it's an inclined plane and the particle falls on the inclined. You expect it to go in the negative x direction. Now in the y direction, the velocity is going to be so we'll take this equation 11 and from there we will manipulate to find out v1y. So v1y is going to be 2v2x cosine theta divided by sine theta minus v0. Yeah. Yeah, so that is 2v2x is 2v0 sine theta cosine theta 1 plus e divided by 2 plus sine squared theta times cosine theta divided by sine theta minus v0. So I cancel the sine theta, and what we have is 2v0 cosine squared theta 1 plus e divided by 2 plus sine squared theta minus v naught. So another step of simplification could be done. We can say that this is v naught over 2 plus sine squared theta times 2 cosine squared theta plus 2e cosine squared theta minus 2 minus sine squared theta. Yep, so that is right. And so as the last step of simplification, I can slightly simplify it, not much. 2 plus sine squared theta in the denominator, and in the numerator it is just going to be cosine squared plus, it is cosine squared minus sine squared. So there is not much simplification that can be done here. Yeah, I would just leave it as it is. So 2 cosine squared theta plus 2e cosine squared theta minus 2 minus sine squared theta. Yeah, unfortunately not much simplification, but that's the expression for the velocity component of this particle. So that's one answer, this is another answer, and this is the third one. So this is the x component of the particle's velocity in after the impact, and this is the y component of the particle's velocity after the impact. So that's it for this video. I may continue with this problem, make some observations, look at certain specific values of theta, and see what kind of velocities we get if we substitute specific values of theta, just to do a little bit more analysis of this problem and interpreting the answers or the solutions. So we can do that in a brief follow-on video. But this is it for this session. So thank you so much.